In this video, we're going to take a look at a couple of intuitive examples utilizing the notion of linear dependence and linear independence. So what we know is that if a vector could be expressed as a linear combination of the other vectors in that set, then that vector is said to be linearly dependent upon the other vector. So let's just say that we're given three vectors here. Maybe the vector 1, 2, the vector 3, 5, and the vector, we'll say 0, negative 1. Now, whenever you have more vectors than you do dimensions, at least one of those vectors will definitely be linearly dependent upon the other. And the notion is that if you have two vectors that, say, span all of R2, meaning that you can scale them and put them together tip to tail to get to any location you want, then the third vector, by intuition, is just going to be some combination of these two, because if these two allow me to get to anywhere I want in two dimensions, that includes the third vector as well, or the point corresponding to the third vector. So the way I've set this up is that we can almost eyeball and see that if I take, let's see, to get the third vector, if I take negative 3 times the first vector, and I add to that the second vector, 1 times 3, 5, that's going to give me, let's see, negative 3 plus 3 is 0, and negative 6 plus 5 is negative 1. So these are going to be linearly dependent because I can write the 0, negative 1 vector as a linear combination of the other two. And so all that really means is that I can scale the 1, 2 vector, scale the 3, 5 vector, and arrive at the position 0, negative 1. So if I take 1, 2, and I take negative 3 times that, let's see, where's that going to land me? That's going to land me somewhere over here. So that's going to give me negative 3, negative 6, so negative 3, and then negative 6, going down 6 units. 1, 2, 3, 4, 5, 6. So that's 3 multiples of this guy. I'll do that in red. 3 multiples of that guy will put me negative 3, negative 6 down here. Okay, now if I add to that 1 multiple of the 3, 5 vector, so from there we're gonna move over 3 up 5. Well, that's gonna land me exactly at the point 0, negative 1. So that's one way of thinking about linear dependence, is that this 0, negative 1 vector, this guy here, can be generated as a linear combination by combining by adding scaled versions of the other two vectors. Now, the other interpretation is that if I can find coefficients, we'll just go ahead and call those x1 times the first vector, which I'll just denote a1, plus x2 times a2, plus x3 times a3. If I could produce the 0 vector by finding some coefficients on these 3 vectors, then that means also that these vectors are linearly dependent. Now, what would that mean? Well, that simply means that if I find the right coefficients here, and that's going to require solving for x1, for 1, 2, plus x2 times our second vector, which was 3, 5, adding to that some combination of, or some multiple of 0, negative 1, can I land myself back at the origin? Okay, well, if we want to solve this as a system of equations, we can write 1, 2, 3, 5, 0, negative 1, and then the 0, 0 vector here. So I'm going to be looking for these coefficients for x1, x2, x3. And if I go ahead and do this, what I'm going to come up with, I'm going to get this as my reduced row echelon form. So what does that mean? Well, right now we can conclude that since x1 and x2 both have rows in which those columns are the ones in which we have the leading 1, x3 is going to be a free variable. And the reason, again, we know that is because x1 is going to equal, or x1 minus 3x3 is going to equal 0. So x1 equals 3x3. x2 equals negative 1x3. And so we see that the values of x1 and x2 are going to be determined by the value of x3. So I'm going to fix x3. I'm going to make it some constant. And this is going to tell me then that my solution for these three coefficients is any point, any multiple of, let's see, this will be 3c negative 1c, c. So basically any multiple of the 3, negative 1, 1 vector. So any multiple of that vector will work as values for x1, x2, x3. Well, if I let c be 1, just to demonstrate this, if I put a 3, if I replace this guy with a 3, and I replace this guy with a negative 1, and I replace this guy with a 1, that's going to give me 3 minus 3 plus 0 is 0. Check. And we have 6 minus 5 is negative 1. Let's see. Oh, yeah, so this was 6 minus 5 is 1, plus negative 1 is in fact 0. And so what we've geometrically done here is we found out that if we take 3 times the 1, 2 vector, which will put me at the position 3, 6, 1, 2, 3, 4, 5, 6. So I'm going to denote that vector in red. So 3 times 1, 2 is going to be this vector right up here. And now we're going to take negative 1 times 3, 5. Okay, so negative 1 times 3, 5 is negative 3, negative 5. So down 3, or over 3, down 5. That'll put me right here. And now, again, what we're just asking for is it possible to combine these three vectors such that we get back to the 0, 0 vector. If I take 1 times the 0, negative 1 vector, well, 1 times the 0, negative 1 vector is 0, negative 1, which will push me back down right towards the origin. So basically another interpretation is, one interpretation is, can we generate one vector out of the other two? And then the other interpretation is, can we combine those three vectors to get back to the origin? And if the answer is yes for one of these, the answer will be yes for the other. And that means that these vectors are, again, linearly dependent. Let's take a look at a three-dimensional problem, a three-dimensional situation. And in this three-dimensional situation, let's take a look at the vectors 1, 2, 0, the vector 0, 0, 4, and the vector 0, 3, 0. Okay, in terms of where these three vectors lie, they lie in different planes. And so I'm going to refer to this as x, y, z, and we're in the positive first plane. Okay, so 1, 2, 0 will be 1 unit in the x direction, 2 units in the y direction, 0 units in the z direction. So that's going to be this vector here. Okay, so 1 unit this way, 2 units, and then the vector is going to be lying inside of that xy plane. So that's as if this vector were lying on the floor in this three-dimensional space. Now we also have this plane right here, which is the YZ plane. We also have this plane here, which is the XZ plane. So this second vector, 0, 0, 4, well, that's 0 units in the x direction, 0 units in the y direction, and 4 units up. So that is going to give me a vector that's going to point straight up, and that's going to be this guy here. So if I think about where I can get to with these two vectors, well, this blue vector will allow me to ride anywhere along this blue line. If I were to extend this blue line infinitely this way and infinitely back the other way, I could travel along that line using just the 1, 2, 0 vector. But I can't get off that line until I access the 0, 0, 4 vector. So if I make it to, say, this point right here, and now I want to get myself off of that xy plane, I can take some multiple of the 0, 0, 4 vector, and that will allow me to travel straight up and down. Okay, so far these are linearly independent because clearly they don't allow me to go in the same directions. One allows me to only go up, one kind of allows me to hover along the floor. This third vector, 0, 3, 0, well, that's going to be 0 units in the x direction, 3 units in the y direction, 0 units in the z direction. So that vector is basically going to lie along the y-axis. All right, so the blue and the green vector kind of allow me to now get anywhere, navigate anywhere in that xy plane, because we could argue that, hey, if you wanted to get off this blue line, then you could travel, say, to this point here, and then I want to get off that blue line, so the green vector will allow me to go directly this way or directly this way, some multiple of that 0, 3, 0 vector. And then the pink vector will, of course, allow me to then, from here I could go up or I could go down. I should have drawn this in pink as well. So at any point I can choose to go up and go down. So the blue vector and the green vector will let me navigate all of R2 in the xy plane, and then the middle vector will allow me to get off of that xy plane, and clearly I can go to whatever z value I want because the vector just goes straight up and down. So the intuition here is going to lead us to the fact that these are going to be linearly independent vectors. So if you think about our one interpretation, can you generate, for example, well, let's go ahead and pick on 1, 2, 0. Can you get to the point 1, 2, 0 right there using just the green and pink vectors? Well, the green vector only allows me to travel along the y dimension. The pink vector allows me to travel along the z dimension. So I'm not going to be able to get here with the pink and the green vector. The only place I'll be able to travel is basically inside of that yz plane. So intuitively speaking, 1, 2, 0, we're not going to be able to get there by using the 0, 0, 4 vector and the 0, 3, 0 vector. So I'm asking, what are those constants that we would apply? Well, if you look at this, and if you try to solve this, if you call this x1 and x2, then there's no way that I'm going to be able to make the top component equal to 1. And in other words, I'm not going to be able to move in the x direction using just the pink and the green vectors. I can only move up and down, left and right. And so if we take some multiple of 0, we're always going to get 0. And if we add that to some other multiple of 0, namely x2 times 0, we're not going to be able to produce a positive 1 like we want by figuring out what to scale these by. Now similarly, you cannot make it to the green vector using only the blue and the pink, because the blue vector will allow you to kind of travel along this diagonal line. The pink vector will allow us to travel up and down, so I won't actually be able to get to this location right here using just the blue and the pink vectors. And if we try to solve this, if we try to solve for x1 and x2, and we set up our matrix something like this, 0, 0, 4, 0, 3, 0, 1, 2, 0, and what I'm asking for is there an x1 and an x2 that will cause this, our reduced row echelon form is going to give us something like, we're going to get a 0, 0, 1 somewhere. One of these equations will cancel out one of the others, and so as a result, actually, well, look at this. Right there it is. That row right there will end up just getting shifted down because it has no leading ones, and so we're going to get the false statement that 0 equals 1. Therefore, it's not possible. So that's the intuition behind the 3 dimensions. Of course, the other interpretation is this: can we take the 1, 2, 0 vector some amount of distance, take the 0, 0, 4 vector some other amount of distance, take the third vector some other amount of distance, and basically get ourselves back to the origin? And the answer is no, because again, if the pink vector will allow us to move up, the green and the blue will not allow us to get back down to the origin. So there's no way that we are going to be able to leave the origin using one vector, go somewhere else with the other vector, and then use the third vector to get us back home. And so in this case, what we would get is, if we solve this system, 1, 2, 0, 0, 0, 4, 0, 3, 0, 0, 0, 0, and again, this is just the coefficients that we're looking for, we are only going to get, there's only one way you could do this, and that's going to be as if you don't leave the origin at all. That is, if all three of your x's, x1 equals 0, x2 equals 0, x3 equals 0, is the only solution to this system. And guess what this is? Well, this is a homogeneous system that we're trying to solve. And in this case, the only solution is that these three planes all intersect at the origin. The system of equations represents three planes in 3 dimensions.